Today we are working on indefinite integral involving exponential and logarithmic function. We are going to go over formulas first. So here in number 1, you can see the most general formula for the integration of exponential function. So the first formula is you have integration of b raised to ax. B is a constant. A is also a constant. If you integrate this with respect to x, the value of integral will be b raised to ax. Whenever we are integrating the exponential function, you will get the exponential function divided by the natural log of the base, so divided by L and B. And also you have to divide by the derivative of this power here, which is a times x. The derivative of a times x is a, because it's like 5 times x is 5, just like that. So a times x is a, so we divide by that, and then plus c. So that is the most general formula for the integration of exponential function. Now, if I substitute this b by the Euler's number e, so if the value of b is equal to e, if b is equal to e, then let's see what we get. Then we get the second formula. It will be e raised to ax, with respect to x. So integration of e raised to ax will be, if I plug in e for b, then it will be e raised to ax, divided by the a as it is, and then it will be natural log of b is e. So natural log of e is 1. So it will be e raised to ax over a, then plus c. So that's your second formula. So if we substitute b equal to e in the first formula, we get the second formula. Now, the most simplified formula is, if I plug in, let me write here, if a equal to 1 in second formula, in this formula, if I plug in a equal to 1, then I get the third formula. It will be e raised to, a is 1 times x is x, e raised to x. When you integrate that with respect to x, it will be e raised to 1 times x, e raised to x, divided by a is 1, divided by 1, it will not change the value, plus c. So integration of e raised to x is e raised to x plus c. So these are the three important formulas for the integration of exponential functions. So after we have these three formulas for the integration of exponential functions, now let's look at the formulas for the integration of logarithmic function. The most general formula is formula number 4. You can see here the integration of log with any base b of x, okay, that is the argument of the logarithmic function, with respect to x will be x log x minus x, we divide by the natural log of b plus the constant of integration. Also in this formula, if you plug in b equal to e, then it will be log with base e, which is natural log x dx, will be x natural log x minus x over the natural log of e, which is 1. So that will be the formula. So these are the 5 important formula, okay, 5 important formulas that we'll be using in solving the examples today. So let's begin with the first example. Here is our first example. Evaluate the following integrals. We have 2 indefinite integrals given here, and we are asked to evaluate them. First, we are going to work on part A. So if we look at part A, we have the integral of e raised to sine x over secant x dx. We are integrating with respect to x. I can rewrite this and make it a little beautiful. So if I want to rewrite this, I can rewrite like this: e raised to sine x. I have secant x in the denominator. That means it is the reciprocal 1 over secant. That is the reciprocal of secant, which is same as cosine x dx. Now, If you examine this formula or this integral, you'll see that you have e raised to sine x. This is the composite function where your inside function is sine x. And you also know that the derivative of sine x is cosine x, which is also here. That means the derivative of that inside function of the composite function is here in this integral, meaning of that is we can use the u substitution to evaluate this integral, where u is the inside function sine x. So let's do that. Let u equal to sine x. Now, if we differentiate on both sides with respect to x, you get du over dx. Derivative of sine x is cosine x. So meaning of that is du equal to cosine x dx. Now we can make that u substitution here. E raised to sine x is u. And then cosine x dx. Cosine x dx is du. Now it is easy to integrate. Integration of e raised to u is e raised to u plus c. So that is equal to, now that is my answer in terms of u. All I need to do is substitute back the value of u, where u is sine x. So it will be e raised to sine x plus c. That means the integration of e raised to sine x over secant x with respect to x is e raised to sine x plus c. Now let's work on part B. In part B, we have to evaluate the integral of e raised to x over 2 divided by e raised to x over 2 plus 1 with respect to x. Now, if we look at this carefully, you can see that the derivative of the denominator, if you look at the denominator, in the denominator you have e raised to x over 2 plus 1. And the derivative of this one will be, derivative of 1 is 0. Derivative of e raised to x over 2 will be half e raised to x over 2. But we don't see that half in the numerator. So what I can do is, I can quickly multiply by half and also divide by half. Dividing by half is same as multiplying by 2. So if I do 2 times half, it is just 1. So nothing is changed. Because by doing this, I can use the u substitution. If u equal to e raised to x over 2 plus 1, the derivative will be half e raised to x over 2. So let me show you over here. Let u equal to e raised to x over 2, or you can write e raised to half x. X over 2 is half x plus 1. If you want to find the derivative of that, du over dx is equal to derivative of e raised to anything is e raised to that quantity. So in this case, e raised to half x, but it's not x, it is half x. So if you want to find the derivative of half x and multiply using the chain rule, the derivative of half x is half. So we multiply by half. The derivative of 1 is 0. So I don't need to add that 0 there. So it will be du equal to half e to the half x, or x over 2 dx. Now I can use this information to make the substitution over here. So if I make that substitution, I have e raised to x over 2 plus 1. E raised to x over 2 plus 1 is u. So in the denominator, I have a u, which is same as 1 over u. And then in the numerator, half e to the x over 2 dx. Half e raised to x over 2 dx is du. So this is equal to 2 times integration of 1 over u is natural log of absolute value of u plus c, because the derivative of natural log of u is 1 over u. I put the absolute value here because the argument of the logarithm must be positive all the time. That's why I'm putting u there, because I don't know whether u is positive or negative without analyzing it. But if I try to analyze this, you can see here, u is equal to e raised to half x, which is always positive, plus 1. That will also be positive. So technically, you don't need the absolute value there because u is always positive. So in next step, I'm going to write that without using the absolute value. And the value of u is e raised to x over 2 plus 1. E raised to x over 2 plus 1 plus c. So the integration of e raised to x over 2 divided by x, e raised to x over 2 plus 1 with respect to x is 2 times the natural log of e raised to x over 2 plus 1 plus c, the constant of integration. Example, evaluate the following integrals. We have two indefinite integrals here. Let's work on part A first. In part A, we have to integrate 3 raised to 4x dx. 3 raised to 4x dx. Now, if you remember from the list of formulas, we have this formula. Let me write that over here. We have integration of b raised to ax dx. If I need to integrate b raised to ax dx, the formula is b raised to ax divided by a natural log of b plus c. That's our formula. So if I use this formula, you can see here in place of b, I have 3, and in place of a, I have 4. So meaning of that is, if I want to use this formula, then in this example, a is equal to 4, and b is equal to 3. So the integral will be 3 raised to 4x dx is equal to, okay, we write b raised to ax, that is 3 raised to 4x, divided by a is 4, natural log of b is 3, plus c. And that is my answer. It is 3 raised to 4x divided by 4 natural log of 3 plus c. You can simplify this a little bit, but if you leave here, that's totally fine. If you want to simplify, this is what you can do. 3 raised to 4 raised to x divided by 4 natural log of 3 plus c. Here we have 3 raised to 4 times x, which can be written as 3 raised to 4, then raised to x. So the final answer will be the integration of 3 raised to 4x dx is equal to, you can see here 3 raised to 4 is 81. So that is 81 raised to x divided by 4 times natural log of 3 plus c. You can leave it here, that's okay. If you want to go further, you can raise this power over here. It will be 3 raised to 4. So if you want to simplify further, it will be 81 raised to x divided by the natural log of 3 raised to 4. 3 raised to 4 is 81 plus c. So we'll not be able to simplify any further. So that is the value of the integral given here in part A. Part B, we have the integration of e raised to 3x plus 1 dx. This integral is very similar to 3 raised to x, but in place of x, I have 3x plus 1. So this is the composite function with the inside function as a linear function. So whenever you are evaluating a composite function with inside function, linear function, you just have to find the integration of outside function and then divide by the derivative of inside function. So outside function is e raised to x. In place of x, I have 3x plus 1. Integration of e raised to x is e raised to x. But in place of x, I have 3x plus 1. Because it is a composite function, we have to divide by the derivative of the inside function. Derivative of 3x plus 1 is 3 plus c. And that is the answer. Example, evaluate the following integrals. Here we have two indefinite integrals given, and these are the integrals involving logarithmic function. Now, before we evaluate the first integral, try to recall the formula. We know that the integration of logarithm with any base b, of x with respect to x is equal to, if you remember, it is x times the natural log of x minus x over the natural log of b, okay, natural log of b, then plus the constant of integration c. That's our formula. So let's try to use that formula over here in part A. So if we use that formula in part A, that is equal to, you can see we have the log with base 3. So our base is 3. And in place of x, our argument is 5x plus 1. So this is the composite function with inside function or linear function. That means after we evaluate everything, we have to divide by the derivative of the inside function. So let's first use this formula. We have x times natural log of x. In place of x, I have 5x plus 1. 5x plus 1 times the natural log of 5x plus 1. That is x log x. Then minus x. In place of x, I have 5x plus 1. So I use that formula, and here it is divided by the natural log of the base. Our base is 3. That is what we do when this x or the argument is just x. But here our argument is 5x plus 1. So we also need to divide by the derivative of the inside function. The derivative of 5x plus 1 is 5. So we divide by 5. So 5 will be there. So that is the answer for the first part. Now let's work on part B. In part B, we have to evaluate the integral, which is natural log of 3x minus 5 dx. Now, if we recall the formula, we have the integration of natural log x dx equal to x natural log of x minus x plus c. That's our formula. So if I want to use that formula over here, you can see in our formula, the argument is x, but here the argument is 3x minus 5. So that's a composite function with inside function as a linear function. So after we apply the formula like this, we have to divide by the derivative of inside function, which will be 3. So if I use that, it will be x log x. X is 3x minus 5. 3x minus 5. Natural log of 3x minus 5. Then minus x. Minus, in place of x, we have 3x minus 5. And then we have plus c. But we have to divide this by the derivative of inside function. Derivative of inside function is 3. So that is the answer for the second part. So in part A, I forgot that a constant of integration. So please add plus c.